In this video, we are going to continue to look for real zeros of a polynomial. So recall, we have the zero product property, which says if we multiply two things together, let's say A times B, and we get 0, then we know then either A is equal to 0 or B is equal to 0. The factor theorem tells us that finding the zeros of a polynomial is really the same thing as factoring it into linear factors. So we're going to use what is called the Rational Zero Theorem to help us find the zeros of a polynomial. So recall, we already looked at this. If a polynomial is in the form of p of x is equal to a sub n, x raised to the nth power, plus a sub n minus 1, times x raised to the n minus 1 power plus plus a sub 1 x plus a sub 0. If those have integer coefficients, then every rational zero of p is in the form of p divided by q, where we find the values of p by factoring a sub 0, so our constant of our polynomial, and we find the values of q by factoring a sub n, the factors of our leading coefficient, a sub n. Really powerful theorem. So if we have a polynomial again, and all of our coefficients are integers, so like ... -3, -2, -1, 0, 1, 2, 3, ... So if that's the case, then if it has a rational zero, it has to be in this form. And so we had already looked at a couple of examples in the previous video, and we're going to look at a couple more examples in this video and a couple of more theorems. So let's look at the following problem. In front of you, it says factor completely p of x, which is equal to 6 times x raised to the 4th power minus 7x cubed minus 12x squared plus 3x plus 2. And so we're going to use that rational zero theorem to help us find the zeros of this polynomial, which will help us to factor this completely. We saw that using synthetic division was really helpful when we found our possible rational zeros. So our possible rational zeros, we want to first look at our values, our factors of our constant, which is 2. So our p-value, our factors of 2, which are plus or minus, so it can be positive or negative, 1 and 2. Q, our factors of our leading coefficient of 6. So this is going to be positive and negative. 1, 2, 3, and 6. Those are all numbers that go into 6 evenly. If we have a rational zero, that theorem told us it's in the form of p divided by q. So this is equal to plus or minus. So starting with the first number of p, we're going to look at 1 and divide it by every number in q. So we have 1 divided by 1, which is going to give us back 1. We have 1 divided by 2, which is 1/2. 1 divided by 3 is 1/3. And 1 divided by 6 gives us 1/6. So now we're going to go to the next number for p, which is 2. And we're going to divide it by each number in q. So we have 2 divided by 1, which is 2. We have 2 divided by 2, which is 1, but that's already in our list right here, and so we don't need to rewrite it. We have 2 divided by 3, which is 2/3. And we have 2 divided by 6, but if we reduce that, that is 1/3, and that's also written already, so we don't need to rewrite things twice. And so we went through and found all the possibilities of p divided by q. And so now let's use the zero remainder theorem. So if we get 0 as our remainder, and then we know the following will give us a factor of our polynomial. So let's try 1. So recall, we're going to put, for the synthetic division, we're going to put our coefficients in descending order of powers, and we're going to put 0 if there was not one of those exponents. That would descending order of powers and there was missing one, we would put a 0 as a placeholder. In this case, we don't have one, but let's go down. So we have 6x to the fourth, so we're just going to put 6, negative 7x cubed, so we're going to put negative 7, negative 12x squared, so plugging in or putting in negative 12, plus 3x, so putting a 3, and plus 2, so putting a 2. We bring down our first number, which is 6, multiply it by the number in our divisor box, which is 1. So 6 times 1 is 6, and then we sum that column. Negative 7 plus 6 gives us negative 1, and we repeat this process. So 1 times negative 1 gives us negative 1, put it underneath the next number, sum that up. So negative 12 plus a negative 1 gives us negative 13. 1 times negative 13 gives me negative 13. Sum this up, I get negative 10. And 1 times negative 10 gives me negative 10, and 2 plus negative 10 is negative 8. Our whole goal here is that we want a 0 for our remainder. And so since our remainder did not equal 0, and that's the last number of our synthetic division, then I know that x equals 1 is not a 0. Of x of p of x. So I would go and I would try this again. So let's try with 2. And so if we put 2 in our division box, again, rewrite down our coefficients of our polynomial. So 6, negative 7, negative 12, 3, and 2. And let's repeat the process, and we hope that we get 0 as our remainder. So bringing down 6, our first number, 2 times 6, that gives me 12. Negative 7 plus 12, that gives me positive 5. 2 times 5 is 10. Negative 12 plus 10 is negative 2. 2 times negative 2 is negative 4. 3 plus negative 4 gives me negative 1. 2 times negative 1 is negative 2. And 2 minus 2 is 0. So that makes us happy that we got a remainder of 0. And so we know that x equals 2 is a factor of p of x. Or is a 0, sorry, is a 0 of p of x. But if we subtract 2 on both sides, that would give us our factor. So x minus 2 is a factor of p of x. So in the previous video that we were making, and unfortunately the power went out, so we got interrupted and the video stopped. Anyways, so in the previous video, we saw that the last numbers on our synthetic division, or the last number, if it was 0, that was the remainder. All the others were coefficients of our polynomial, which was 1 degree less. And so this is a degree 4 polynomial. And so the bottom row is 1 degree less than the 4. And so this is going to give us 6x cubed plus 5x squared minus 2x minus 1. And so we're going to want to repeat this process. Right now we know this times the factor of x minus 2 is equal to P of X. So we want to repeat this process, and we want to factor down 6x cubed plus 5x squared minus 2x minus 1. I know that if I tried a factor before, or a zero before, and it didn't work, then it's not going to work in this original one. It is what we have left here, our quotient. It is possible that a zero occurs more than once, and so I may want to try 2 again. I would use it, though, with a polynomial that I have here. But thinking about it, I don't think 2 is going to work, or I know 2 won't work, just by my rational zero theorem. And if I think of -1 as my constant, my p-value, it's just plus or minus 1. So maybe, because I don't want to try fractions if I don't have to, let's try -1 instead. And so I'm going to put -1 up in this box, division box, and we're going to use the coefficients of this quotient here. So 6, 5, -2, and -1. So bringing down our first number of 6, 6 times -1 is -6. 5 minus 6 gives me -1. -1 times -1 is +1. -2 plus -2 plus 1 is -1. -1 times -1 gives me +1. And we get 0. So awesome, we got 0. So we know that x equals -1 is a 0 of that polynomial. And that tells me that x plus 1 is a factor. So let's break down our polynomial of p of x a little further. So we have p of x is equal to this linear factor of x minus 2 times our linear factor we just found, x plus 1, times the quotient. So our quotient down here, it's 1 degree less than what we were starting with, and we were starting with, in this case, a cubic. So this will be 6x squared minus x minus 1. So our rational zero theorem only gives us the possible rational numbers. It doesn't give us any numbers that were irrational, like the square root of 2, or it doesn't give us any complex numbers or imaginary numbers as zeros. I noticed that my quotient here, 6x squared minus x minus 1, and this is a quadratic, so we can use our tools in the past to find the 0 here. So we can use our quadratic formula. I'm looking at it, and it doesn't look factorable. So let's look at the quadratic formula to see if this has any real zeros. So I have, again, 6x squared minus x minus 1. I'm curious about when this is equal to 0. So using my quadratic formula, I know x is equal to -b, so negative of -1, plus or minus the square root of b squared, so -1 squared is 1, minus 4 times a, which is 6, times c, which is -1, all over 2 times a, which is 6. So x is equal to 1 plus or minus the square root of 1 plus 24, all over 2 times 6, which is 12. So we get x is equal to 1 plus or minus the square root of 25, all over 12. So x is equal to 1 plus or minus the square root of 25 is 5, all over 12. So looking at this, we have 2 separate numbers. We have x is equal to 1 plus 5, which is 6 all over 12, which is 1/2. And we have x is equal to 1 minus 5, so that's -4 all over 12, which reduces to -1/3. So those are rational zeros. And notice those are 1/2 is in our list, and -1/3 is also in our list because it's plus or minus out here. So looking at the linear factors, I could rewrite this. This is x equals 1/2. I could subtract 1/2 on both sides and say x minus 1/2 is a linear factor, or I can make it a little nicer so I don't have to look at fractions. We can multiply both sides by 2. We got 2x equals, the 2's cancel here, 1. Subtract 1 on both sides. I know 2x minus 1 equals 0. So 2x minus 1 is one of those factors. And for the factor of x equals -1/3, so we can do that same process. Let's clear our fraction, multiply both sides by 3. So we get in here 3x is equal to -1. Add 1 to both sides, I get 3x plus 1 equals 0. And so the other factor here is 3x plus 1. Bringing down our other factors we already found, x plus 1 and x minus 2. We found the p of x as a product of linear factors. And just so we can see them, our zeros were x equals -1, x equals +2, x equals 1/2, and x equals -1/3. So these are places where our graph would cross the x-axis, because if you look at above, we talked about multiplicity of factors before. The multiplicity, those factors occur one time, which is odd. Odd multiplicity tells us that it crosses the x-axis at those values. So the rational zero theorem gives us a way to break down and factor polynomials. Notice that if we had lots of factors, though, or things in the form of P over Q, we could have to go through and test a lot of numbers before we find them. And so there's some rules here that will even help us narrow down those numbers even further. And so let's look at those rules. So the first rule in front of us is the upper and lower bound theorem. So what does it mean, first of all, to be an upper bound or a lower bound? So reading what is in front of us, it states, if every real root c of a polynomial equation satisfies where a is less than or equal to c is less than or equal to b, then we say that a is a lower bound, and we say that b is an upper bound. So if we find some number c, we might have a lower bound or an upper bound, A or B. To see if we have a lower bound or upper bound, it's possible that we use this upper and lower bound theorem. The following states, let P be a polynomial with real coefficients. And so we're only doing this if our coefficients in front of our variables of the polynomial are real. In the next chapter, we might see cases where that's not the case. And so if we divide P of x by some factor x minus b, so with our value b being greater than 0, and we're using synthetic division, we want to watch the bottom row of our synthetic division. So, and if the bottom row contains the quotient, which we know that the bottom row is the quotient, and the remainder has no negative entry, then we can say B is an upper bound for the real zeros of P. So if you're looking at the bottom row of synthetic division and you notice they're all positive numbers, then we know that that's an upper bound and we don't have to check any numbers that are greater than that. So to check for lower bounds, again, we want to look at the bottom row of our synthetic division to see if the number we're checking is a lower bound. And so if we divide, let's say P of X by X minus A, where A is less than 0, using synthetic division, so we're plugging in a negative number when we're using the synthetic division. And if the row contains the quotient and the remainder has entries that are alternating between non-positive and non-negative. So if it's alternating in signs, then A is a lower bound for the real zeros of P. When you're doing this, if you have 0 as one of your entries and the quotient as your coefficient, or we can say, I guess, the 0 of the polynomial, if it's a 0 of the polynomial and our remainder is 0, no, 0 is considered either positive or negative as needed for this theorem. So our next theorem that we're going to look at, and we'll look at this theorem that we just said as we're trying to find zeros of a polynomial. We'll talk about it as we're doing that. But this is a theorem that we can keep in mind while we're finding those zeros. The next theorem that we're going to look at deals with variations of signs, and it's Descartes' Rule of Signs. And the following, we need to know what it means by variation of signs. So let's read what this states. It states that variation in signs. If P of X is a polynomial with real coefficients, written in descending order of powers of X, and omitting powers with coefficients of zeros, then a variation in sign occurs when the adjacent coefficients have the opposite signs. So looking at some following examples, let's determine the variation of signs for each polynomial that we have. And so if we have the polynomial, let's say x squared plus 4x plus 1, let's say that's equal to f of x. Then looking at the coefficient in front of x squared, we have 1. And then the coefficient in front of the x is 4. So notice those are both positive numbers, and that is not changing in signs. And then if I go from the coefficient of 4 to 1, that's also both positive, and that's not changing in signs. And so the number of variations of signs for this polynomial is 0. So looking at the next polynomial, let's call it f of, or maybe let's call it q of x. So looking at q of x and seeing how many variations of signs this polynomial has, we have 2x cubed, so I have a positive number plus 1x. So notice that x squared is missing, but if we go back up to the variation of signs, it says omitting powers with coefficients of zeros. So we don't have to worry about that we're missing a power. So here, 2 to 1, there's no variation in sign. But if I go from 1 to my constant of -6, this is a variation in a sign. 1 is positive, 1, and 1 is negative, -6. And so there's 1 variation in this sign, or in this polynomial. So one more example. If you're looking at the following, x to the 4th minus 3x squared minus x plus 4. And we wanted to count the variation in signs. And let's say that this is equal to g of x. So we got 1 in front of the x to the fourth. We have a -3 in front of the x squared. This is varying in a sign. One's positive, one's negative. -3 to -1, that is not varying in a sign. I put 0 if it doesn't, and 1 and below if it does. -1 and 4, that is a variation in sign. Counting the number of changes, there are 2 changes, 2 variations of signs. So this is going to help us with Descartes' Rule of Signs. And so let's look at what that states. In front of us is Descartes' Rule of Signs. The following states, if p of x is a polynomial with real coefficients, so that needs to hold in order for this to be true, we say the number of positive real zeros of p of x is either equal to the number of variations in the signs of p of x or less than that by an even whole number. And we'll talk about that and what that means in a minute. The number of negative real zeros of p of x is either equal to the number of variations in signs of p of -x or is less than that by an even number. So we want to look at an example and talk about what that means by the number of variations of signs or that number less than an even number. And so the following example, we have Descartes' rule. We want to use Descartes' rule of signs to determine the possible number of positive and negative real zeros of the polynomial. So for the possible positive zeros, and this tells us, again, that we want to look at the number of variations of signs in p of x. So let's first do that. So we have p of x is equal to 3x to the 6th plus 4x to the 5th plus 3x cubed minus x minus 3. And so going from 3x to the 6th plus 4x to the 5th, notice there's no sign change there. 3 and 4 are both positive. 4x to the 5th to 3x cubed, that is not a sign change. 4 and 3 are both positive. But from 3x cubed to -x, we have one sign change. And from -x to -3, there is 0. So the number of sign changes is equal to the possible number of positive zeros. And so we have one possible positive 0. If I subtracted an even number from 1, that gives me a negative number. And that's not possible to have a negative number of zeros. And so from this rule, Descartes' rule of signs, I know that there's one positive real zero. So I know also when I find a positive real zero of that polynomial, I can stop looking for any other positive numbers in my list. So now let's look at the possible number of negative real zeros of p of x. So in order to do this, we need to look at the number of sign changes of p of -x. So for our possible negative zeros, real zeros, I first need to look at p of -x. So I'm going to go in here wherever I see an x in p of x, I'm going to put parentheses, and then I'm going to drop in -x. So I have 3 parentheses because I have an x raised to the 6 plus 4 parentheses raised to the 5th plus 3 parentheses raised to the 3rd minus x. So minus parentheses minus 3. So now let's go in and plug in negative x wherever we have our parentheses. And then let's go and simplify. So I know that p of negative x is equal to, well, if I take negative x and I multiply it by itself an even number of times, that negative 1 times negative 1 times negative 1 times negative 1 6 times is going to be positive because that's even. And so this is the same thing as 3x to the 6. When I multiply, though, negative x an odd number of times, that's negative. So that's like negative x to the 5th power times that 4 in front. So this is going to be minus 4x to the 5th. So going to the next value, I have plus 3 and then times negative x cubed. So that negative x is raised to an odd power. So I'm going to pull the negative out front, and this is going to give me minus 3x cubed. Minus a negative x, minus a negative is plus, so plus x minus 3. So let's go through and count the number of sign changes of p of negative x. So we have a 3x to the 6th to minus 4x to the 5th, that's 1, 0. Negative 4x to the 5th to negative 3x cubed, those don't have a sign change. Negative 3 x cubed plus x, that is a sign change. And a positive 1x minus 3, that's another sign change. And so counting the number of sign changes here, I have 3. So I am going to take that number of sign changes and I'm going to subtract 2 from that. So 3 minus 2 tells me that's 1. If I subtract another even number from 1, I would get a negative number. So there are 3 or 1 negative zeros. So I know if I found 2 negative zeros, I know because of this rule that I would have 1 more. So this is just a way to kind of narrow down our search to find those zeros of our polynomial. So there's a theorem in front of us that states the number of real zeros. A polynomial function cannot have more real zeros than its degree. So looking at the degree of our polynomial, the highest integer exponent, non-zero integer exponent, if it was not an integer exponent and it was negative integer, it wouldn't be a polynomial. But if it's a polynomial function, then we cannot have more real zeros than its degree. So let's put together what we've just been talking about, and let's look at another example, and let's use these rules to help us limit the number of possible zeros that we can have. So the example in front of us states, find all the real zeros of a polynomial and rewrite it as a product of linear and or irreducible quadratic factors. And so we're looking at the polynomial f of x is equal to 2x cubed minus 4x squared minus 10x plus 20. So I would first look at my possible rational zeros. But before I did that, I noticed that all my terms have a 2 in common. And so let's first factor out a 2. That could make our life a lot easier. And so if we factored out a 2 from all of those terms, we would be left with x cubed minus 2x squared minus 5x plus 10. And so now let's look at the possible rational zeros of that polynomial. So I'm actually just going to look at the factored form, I pulled out that 2. And so if I look at my p-value, in this case, I would only have to look at 10 instead of 20 above, pulling out that 2. So I'm going to give me less numbers that I have to deal with. And so numbers that go evenly into 10 are plus or a negative 1, 2, 5, and 10. Pulling out our coefficient of 2 made our Q value equal 1. That is the nicest case. And so our Q value are positive or negative 1. And so now looking at P divided by Q, these are going to give us all the possible rational zeros. So looking at 1, 1 divided by 1 is 1. Looking at 2, 2 divided by 1 is 2. Looking at 5, 5 divided by 1 is 5. And looking at 10, 10 divided by 1 is 10. So if Q is 1, basically we get everything, and that is in our list of P. So now looking at this, let's look at the possible number of positive real zeros. And we can do that by looking at Descartes' Rule of Signs. So again, I'm just going to look at the factored version. And let's go through and count the number of variations of signs. And so we have a 1x cubed to a negative 2x squared. And that changes signs, so that's 1. A negative 2x squared to a negative 5x. Negative 2 and negative 5 do not change signs. And then I have a negative 5x to a 10 that changes signs. So I have 2, or subtract an even number. I just keep subtracting 2 until I get to 0 or a negative number. And if I get to a negative number, I stop. So 2 minus 2 is 0. So this tells me there's 2 or 0 possible positive real zeros. So if I find one, I know there's another one out there. And so now let's look at the possible number of negative real zeros. And so again, we want to use Descartes' Rule of Signs, but now we want to look at what is f of negative x. So this is equal to, don't forget the 2 out here, 2 all times. Now we're going to plug in a negative x wherever we see an x, and then we're going to simplify it. So we have 2 all times negative x quantity cubed minus 2 times the negative x quantity squared minus 5 times negative x plus 10. So simplifying this a little bit, I have my f of negative x is equal to 2 all times, well, negative x quantity cubed is the same thing as negative x cubed. Negative x quantity squared is the same thing as x squared times the negative 2 out front gives me negative 2x squared. Negative 5 times negative x, this gives me plus 5x, and then plus 10. So counting the number of sign changes of that factor, we have a negative x cubed to a negative 2x squared. That's not a sign change. A negative 2x squared to a 5x. That is one sign change. And then I have a 5x to a 10, which is not a sign change. So from Descartes' Rule of Signs, I know that there is one negative real zero. Okay, so now let's start testing. And let's be aware of the bottom row of our synthetic division. And while we're being aware of that bottom row, we can see if the number we're testing is an upper bound. If we're testing a positive number and we get a row of all positives, we know that's an upper bound and we don't have to check any number higher. Or if it's a lower bound, if we're checking a negative number and we get alternated signs, then we know that that's a lower bound. There's no number smaller than that. And so looking at our list, let's plug in our coefficients of the factored form that we have of f of x. And so looking at that those coefficients, we have 1, -2, -5, and 10. And then let's check one of our numbers. Well, I know that there's a negative number in there, so we might want to check for negatives first. So let's try -1. So bringing down our first number, 1. 1 times -1 is -1. -2 plus -1 gives me -3. -1 times -3 is 3. -5 plus 3 gives me -2. -1 times -2 is 2. And this gives me 12. Okay, so they're not alternating in sign, so that's not a lower bound. And I did not get 0 as my remainder, the last number in the synthetic division. So I know x equals -1 is not a 0 of that polynomial. So I'm going to try the next number in my list. So let's try -2. Again, we're using the coefficients of the factored form when we pulled out the 2. So 1, -2, -5 is the upper row of synthetic division. We're going to bring down our first number, 1. So -2 times 1 is -2. -2 plus -2 is -4. -2 times -4, that is 8. -5 plus 8, that gives me 3. -2 times 3 gives me -6. 10 minus 6 gives me 4. So I noticed that we're not alternating in signs for all the things. And I didn't get 0 as my last number. And so I know -2 is not a 0. So next number would be -5 in my list. So -5, top row, -2, -5, 10. Bringing down the 1, -5 times 1 is -5. -2 plus -5 is -7. -7 times -5 is 35. -5 plus 35 is 30. -5 times 30 is -150. 10 plus -150 is -140. So notice here, I have alternating signs. 1 to -7 is alternating, -7 to 30 is alternating, 30 to -140 is also alternating. So this tells me it's not a 0, but -5 is a lower bound. So I know that there's not, -10 could not be a 0. And so you might be thinking, well, we saw that there was one negative real 0 when we used Descartes' Rule of Signs, and we just checked all of the negatives that were possible, and we didn't find one. Well, remember, the Rational Zero Theorem is only giving us the possible rational zeros, and it's not telling me if there are any irrational zeros. So I'm kind of out of luck with what I just did, and so I need to go and let's now test for our positive numbers. And so let's look at +1. Our top row of synthetic would be 1, -2, -5, and 10. Because I'm using a positive number, I'm being cognitive of my bottom row of synthetic division. and looking to see if they are always positive. If so, then I know the number I'm checking is an upper bound. So bringing down 1, I have 1 times 1 is 1, -2 plus 1 is -1, 1 times -1 is -1, -5 plus -1 is -6, -6 times 1 is -6, 10 plus -6 gives me 4. So 1 does not work. I'm going to look at 2 now. I have, because the coefficients 1, -2, -5, and 10. Bring down 1. 2 times 1 is 2. -2 plus 2 is 0. 2 times 0 is 0. -5 plus 0 is -5. 2 times -5 is -10. 10 minus 10 is 0. So I'm really happy that I got a 0 as my remainder. So x equals 2 is a 0. So that means that x minus 2 is a factor. So let's go back and let's rewrite our f of x with that as a factor. And we are given this bottom row is our quotient. And so right now we have f of x. This is equal to the 2 that we pulled out, all times our x minus 2, the factor we just found, all times, so looking at this bottom row, I'm 1 degree less than the top row. That degree was degree 3. So 1 degree less would be an x squared. So this would be 1x squared. So x squared plus 0x, so I don't have to write that, minus 5. And so the quotient, that bottom row, I have a quadratic. And so since it's a quadratic, I can find the zeros by using the quadratic formula, or notice that x squared minus 5, this is a perfect square. I could add 5 to both sides. Squared equals 5. Take the square root of both sides, but remember, if we take the square root, we need to put plus or minus in front of the one side. So x is equal to plus or minus root 5. But notice that we can think of 5 as a perfect square of square root of 5 times square root of 5, right, is equal to 5. And so we can think of this as x minus root 5 all times x plus root 5. So we have f of x is equal to our 2 all times x minus 2 all times factoring x squared minus 5. We just saw that's the same thing as x minus root 5 all times x plus square root of 5. So looking at this, we just factored it as a product of linear factors. And we can tell that our zeros are x equals 2, x equals root 5, and x equals negative root 5. And so our possible positive real zeros said there was 2 or 0. We found that there were 2 of them, which are 2 and root 5. And our negative real 0 was negative root 5. So there is one more theorem in this section that we're looking at, finding the real zeros of a polynomial, that is helpful and that you'll see again when you get into calculus. And the following theorem is our intermediate value theorem. And the intermediate value theorem states, let f denote a polynomial function if a is less than b, and if f of a and f of b are opposite signs, so one's positive, one's negative, then there's at least one real zero between a and b. So this makes sense. Think about it. We know that polynomials are continuous functions. So there's not going to be ever any jumps. There's not going to be any asymptotes. And so if we have some value a, which is smaller than b, and let's say that one of them is positive, so maybe f of a is a positive number, and f of b is a negative number, then because this is continuous, this must cross at least once. So here's an example of it crossing once. But it's possible that it crosses more than once, right? So like example I just drew crossed 3 times. But we know that there's at least one real zero between those two values. And so let's now look at an example. And so the following example says, show that all real zeros of the polynomial p of x equals x to the fourth minus 3x squared plus 2x minus 5 lie between x equals -3 and 2. Well, that's actually something different than I thought, but let's do that anyways. Okay, so first of all, let's look at p of -3. Remember, there was a rule that said that if we want to look at f of c, this was equal to the remainder of x minus c, dividing into our f of x. So we can technically use synthetic division to find that, or you can just plug in -3 wherever you saw an x, and you should get the same thing. So let's use synthetic division just to do that. And that's a little faster sometimes. So bringing down our 1, -3 times 1 is -3. -3 plus -3 is -6. -6 times -3 is +18. 2 plus 18 is 20. 20 times -3 is -60. And -5 plus -60 is -65. So p of -3 should give us back -65. So now let's look at when x is 2. So if I wanted to look at p of 2, I can put 2 in my division box. I have 1. Oops, I made a mistake though. Notice back above, we need to put zeros in the position if there is a number missing, and I did not do that, so let's go back. So I have x to the fourth minus 3x squared. And so I'm missing a cube. So I have 1, 0, -3, 2, -5. So bringing down 1 times -3 is -3. 0 plus -3 is -3. -3 times -3 is 9. -3 plus 9 is 6. -3 times 6 is -18. -18 plus 2 is -16. -16 times -3 is +48. 48 minus 5 is 43. So now let's check 2 and find out what p of 2 is. And so we have 1, 0, -3, 2, -5. Bringing down 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. -3 plus 4 is 1. 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 8. -5 plus 8 is 3. Okay, so this example does not use the intermediate value theorem and the fact that p of 2 is 43 and p of 2 is 3 And so P of 2 equals P of 3. I'm sorry, P of 2 equals 3. And P of negative 3 equals 43. And so notice those are the same sign. So I don't know by the intermediate value theorem, there's a 0 in between. But by the upper bound, lower bound theorem, I actually do know, because I know if I plug in a negative 3 in my divisor box and they're alternating in signs, which I am, 1, negative 3, 6, 6, negative 16, negative 16, 43. Those are all alternating signs. And so I know by the lower bound theorem that x equals negative 3 is a lower bound. If I look at 2 is a positive number. And if I look at the bottom row, my synthetic division, I see that those are all positive numbers. And I know by the upper bound theorem x equals 2 is an upper bound. So we could find all the zeros, but it just wanted us to show that all the zeros of the polynomial are going to have to lie between negative 3 and 2. So if you were using the intermediate value theorem, and let's say that you plugged in a value A, which was less than B, and you found out that the f of A and f of B were opposite signs, and you wanted to find those zeros in between, you can use the following to help you narrow down your search. So in front of you are steps for approximating a real zero of a polynomial. So if you find two consecutive integers, let's call them a and a plus 1, for which f has a real zero between. So f of a gives us one sign, positive or negative, and f of a plus 1 gives us a different sign. We know by the intermediate value theorem that there is a number in between. We could subdivide our interval a plus 1. We can subdivide that into 10 equal intervals, subintervals. And then once we do that, we can evaluate the endpoints of our subintervals until the signs of f change. And then by the intermediate value theorem, then we can say this interval contains a real zero. Now divide the new subinterval into 10 equal subintervals and repeat that process. And we can continue to repeat that process, step 3 and step 4, until you have your desired accuracy. So note if that step 3, the value of f equals 0, the process ends since the value is 0. So we found that 0 in there. So now let's look at an example of what we were just talking about. So we have f of x is equal to 8x to the 4th minus 2x squared plus 5x minus 1. And we want to use the intermediate value theorem to show that we have a 0 between 0 and 1. And so we're going to want to look at what is f of 0. If we go in and plug in 0 wherever we see an x, all we're going to be left with is our constant negative 1. Now let's look at f of 1. So going in, I'm plugging in 1 wherever we see an x. We got 8 times 1 to the 4th minus 2 times 1 squared plus 5 times 1 minus 1. Well, 1 to the 4th, or 1 to any power, is 1. And so we have 8 times 1, which is 8, minus 2 plus 5 minus 1. So 8 minus 2 is 6. 6 plus 5 is 11. And 11 minus 1 is 10. because we have a polynomial, f of x, we know polynomials are smooth and continuous. And f of 0, we have -1. And f of 1, we have 10. They're opposite signs. And so we know that there's a 0 between 0 and 1 by that intermediate value theorem. And so if we wanted to, we could find out where that 0 is and we can round it. So if we break this down into some subintervals, so what about from 0.1 to 0.9? So this is where having a calculator or a graphing utility could be helpful and help us limit the time on doing this. So let's pull that up and let's check and use that to approximate a 0 in between 0 and 1 for f of x. So in front of us, I pulled up Desmos. I plugged in our formula. F of x is equal to 8x to the fourth minus 2x squared plus 5x minus 1. And we were checking to see between f of 0.1. We wanted to see if that was positive or negative. So notice that's negative, and I know f of 0 was also negative. And so let's look at f of 0.9. Actually, let's look at f of 0.2 and see. Notice that that's also negative. So I know that it's between 0.2 and 1. 1 was a positive number. If I look at f of 0.3, notice that I've changed between 0.2 and 0.3. I have a negative number for 0.2, but f of 0.3, I have a positive number. So I know I have a 0 between 0.2 and 0.3. And so let's break down between 0.2 and 0.3. So what about f of 0.21? Okay, so f of 0.21, notice, is negative. F of 0.2 was negative. So that's not going to work. So what about f of 0.22? So notice that that's positive. And so I know that I have a 0 between 0.21 and 0.22. So we can go even further if we wanted to. We can look at 0.211, but we've rounded approximately that our decimal, our value, was going to be x, or 0 is approximately. (0.21). So we just learned techniques to help us find zeros of a polynomial function with real coefficients, and used those rules to help us narrow it down, our search, and help us find those zeros. Those zeros, again, are values where we're going to either touch or cross the x-axis. So this is going to help us to graph our polynomials.